Very generous introduction. Great to be here and talking to all of you guys. Yeah, so actually this is the first presentation of this work, which we started only a month and a half ago or so, specifically because we wanted to be able to talk about something related to approximations from an economist's point of view in this audience. And one of the things that distinguishes the points of view, I mean, we each try to link to different parts of our literature, is that the problems that when you work on an individual problem, a knapsack problem or some combinatorial optimization, among computer scientists and among engineers, typically you isolate that problem and you look at it by itself. And economists try to understand how, for example, each market relates to other markets and how things connect. So we decided that we were going to work on investments, the incentives for investments that are provided by approximation algorithms and certain optimization problems. So the talk I'm giving today, which is joint work with two former students of mine, Mohammed Akbarpour and Chengwu Li, is about the investment incentives that you get from using approximation algorithms in what I'll call a generalized knapsack problem. Now, everybody in this room knows what the standard knapsack problem is. You have a bunch of items, they have values and sizes, and a knapsack of some size, and the object is to pick the feasible collection of items that's no larger than the size of the knapsack to maximize value. We're going to call this thing, the language we're going to use is this is an instance. By a problem, we'll speak of a collection of instances, and you'll see where that comes in pretty soon. The generalized knapsack problem is almost the same, except that now instead of just putting a size on the knapsack, this thing, what happened here? There's a piece missing. There it is. We can have size, shape, weight, and all kinds of constraints here. And so in general, the knapsack, there'll be some feasible collection of subsets, a subset of the power set of n that can feasibly fit into knapsack. And we're just trying to maximize the total value subject to these more general constraints. Okay, so that's what I'll mean by a generalized knapsack problem. Now, many of you will know how we came upon this problem, especially Neil out there, where we encountered problems like this when we were doing the incentive auction, where the object was to see whether it was possible to fit a certain collection of television stations, to assign channels to TV stations so that they all fit without creating interference among one another in a way that maximized the total value of the stations that were left on air, and then we had to buy the other stations to get them off the air. So in this particular case, there were about 2,500 stations. This is a graph of the so-called co-channel interference constraints. It means that each node in here represents a television station. Each arc represents a pair of stations that can't be assigned to the same channel without creating interference. The stations are, in some sense, too close to each other. And the goal is to maximize the total value of the stations that are selected to remain on the air using just some subset of the channels that were available before. And this just checking feasibility for stations is a graph coloring problem. That is, if you think of each channel as representing a color, then the question of whether it's possible to assign channels to stations is the same as the question of whether it's possible to assign colors to nodes so that no two connected nodes are the same color. This is just an approximation of the actual constraints, but gives you a good idea of what the problem was like. And the point is that these problems are hard, and we use approximations. And we often use approximations then in hard problems, and we want to know how that fits in with the rest of the economic system and affects its performance. So what our paper is going to do is we're going to look at a generalized knapsack problem. That I've defined that for you already. I'm going to use the problem again, I'm reminding you, to mean a collection of instances. We're going to look at monotone algorithms that guarantee some fraction of the optimum for some problem, that is some class of instances, some fraction beta greater than 0 of the optimal value, and that can be implemented because the algorithm is monotone by a threshold auction. For those of you who don't know what that means, I'll quickly go over it again in a few slides. About half this talk covers the background and half covers what's new. And we're going to let one of the players invest, pay a cost to raise her value in this procedure. And the main results are going to be these. For any beta less than 1, there's a problem and a monotone algorithm that has a guarantee of beta, but has no strictly positive guarantee at all when investments are possible. Second, for any monotone algorithm that satisfies a simple condition that we're going to introduce, the algorithm's beta guarantee, whatever that beta might be, also extends to the related problem with investments. So there's an additional property that the algorithm has to have in order for its computational guarantee to apply to the extended problem with investments. And then there's going to be a variation of the condition that's sufficient and nearly necessary, but not an especially useful condition because it's not going to be easy to check, but essentially something that gives you an idea of that we're getting close to a necessary and sufficient condition for the to be able to generalize in this way. Okay, so that's what our paper will do. Let me quickly go through 2 parts of background. A lot of this is just definitions and notation. So first of all, by an instance of a packing problem, we're going to mean a pair, which is values for each of the items and some set of feasible constraints represented by a set F, in which V is the vector of values and F is the set of feasible packings. An allocation problem is going to be a collection of instances. So it might be we're packing knapsacks with only small items, and that would give us an example of a problem, in which case we'd get really good approximations. And an allocation function is going to be a mapping from instances from the problem into subsets of that. That's the power set of n, that's P of n, that maps instances of the problem into feasible allocations. So f of little v in script f is an element of script f. It's some feasible allocation that's selected by our allocation function. Okay? So examples, opt, which is the allocation function that maps each instance into an optimal solution, it's a familiar allocation function. Greedy is the allocation function that for the standard knapsack problem that selects a solution by greedily selecting the items that have the highest value per unit size, the Danzig's greedy algorithm. And mgreedy is the allocation function that selects the greater of the greedy solution or the most valuable individual item. Okay? Yeah? Just
to be sure, your problem in general also includes the independent set forming, for example. So it's hard to approximate. Yeah?
It can be hard to approximate, yes. So, and we're going to say that the surplus that's associated with an allocation function for some instance is going to be denoted by SFI. So f again is the function and I is the instance. And you take a look at the total value of the things that are selected for that instance, and that's what we'll call the surplus. I guess it's more common in this group to call it the welfare. An allocation function is said to be a beta approximation for the problem omega if for all instances in omega, the surplus you get by applying f is at least beta times the optimal surplus. Okay? Okay, and just these things should be hopefully familiar, so I'll go off this quickly. If you have a standard knapsack problem, you might have a collection in which the sizes are constrained, so the individual items are no more than a fraction lambda of the total size of the knapsack. In that case, the greedy algorithm guarantees you a fraction 1 minus lambda of the optimal value, and mgreedy guarantees you a fraction that's the larger of a half, or 1 minus lambda of the optimal value. And corollary, of course, is that in the unconstrained knapsack problem, that is when lambda is 1 and you don't impose any limits, the greedy has a guarantee of 0, and mgreedy has a guarantee of a half. Okay, this is just background. Okay, so that's that part of the notation. For those of you who don't know, there's been a few references to this already today, but implementation using auctions. And So a direct mechanism, which I think everybody here probably knows, is a pair FP consisting of a monotone allocation function and a rule for selecting prices. And the allocation function is monotone if whenever you increase the value, starting from any value and any feasible set, if you increase the value of item n, if it was selected with the lower values, it's still selected with the higher values. Okay? And opt and greedy and mgreedy are all examples of monotone allocation functions. And the reason we're interested in monotone allocation functions comes here. Direct mechanism is called a threshold auction. If f is monotone and the payments are given by this formula, so p super f sub n is the payment under the mechanism associated with f when for individual n, and it's 0 if n is not selected. And if n is selected, then it's the lowest value that f could have reported and still be selected. So this is the lowest number x that player n could have reported and still been selected as a winner. And the theorem is if f is a direct mechanism in which losers pay 0, then it's truthful if and only if it's a threshold auction. That is, you can construct these things only for monotone f, and the way you construct them is you charge everybody the lowest value they could have had and still have been packed into the generalized knapsack. Okay? Okay, so that's my treatment of the background. I hope that's all familiar, and now let's get to the part that's new. New stuff, okay? So we're going to talk about investment incentives, and as economists, the reason we're interested in them, and this is everywhere, I mean, all the problems we're interested in looking at, if we're looking at a TV station looking for broadcast channels, well, it's going to make investments in equipment and programming and advertising, and if it has to make that beforehand, it wants to take into account what's going to happen in the allocation mechanism. If we're allocating airline landing slots, the airlines are going to invest in airplanes and marketing and slots in other airports. If we're looking for allocating time on a supercomputer, the analyst is going to invest in software and other related analyses. If a manufacturer is seeking time on a specialized machine, I mean, you know, on and on, all these problems that we're looking at that are normally analyzed in isolation, they're actually all part of a larger economic system. People are creating these assets that are being allocated, and we want to know, if you allocate this way, what happens to the investment incentives. Okay? Okay, so here's our formulation. And this is, again, we've only been at this for less than 2 months, so this is a full information formulation. It works like this. We're going to take a look at one bidder, bidder 1, who can invest some amount C, which is some non-negative number, to increase its value from V1 of 0 to V1 of C, where, and we're going to restrict this since we're going to be expanding our allocation problem, we're going to restrict this so that after he's invested, we're still in the same class of problems. So in general, he's going to be increasing his value, and we're going to be looking at classes of problems so that after the investment, his value is still in the same class. Okay, and bidder 1 we're imagining is facing a threshold auction and is going to maximize its payoff. It's going to decide how much to invest. To maximize it, how much am I going to invest in aircraft or in programming or whatever, to maximize my payoff, and we're going to do it in the full information case, that is knowing V1. In general, we're going to want to look at this investment later on with uncertainty about others' values, but the analysis here today will all be the full information version. And our notation is that what we're going to call the investment technology, delta C, is just V1 of C minus V1 of 0. So delta of 0 is 0. It's how much you increment your value by making an investment. The investment that bidder 1 is going to choose is CF, which is defined to be anything, well, that it's going to maximize his payoff. And what is his payoff? He's going to choose a C greater than or equal to 0 to invest. That'll make his value V1 of C. If he wins, he's going to pay P1, which is going to be a function of everybody else's value. And he's going to get this amount if he's selected. So if bidder 1 is one of those who's selected after the investment, and in any case, he's going to incur a cost C. Okay, so that's just bidder 1 maximizing his expected payoff. And the efficient investment is C star, which is the thing that maximizes the surplus under opt in the same problem, but using opt here. Okay. All clear? All right. So the first thing you need to know about this is that we really don't have to look at lots of different investment possibilities. There's only going to be 2 possibilities, both for the optimum and for the investment that the bidder himself makes. So we're going to assume, for simplicity here, that the maximizer is a singleton. Otherwise, there's some additional notation to write down. We're going to assume that the maximizer is a singleton, and it's denoted by K. K is we're going to assume K is a positive number. Investing increases your value by, investing optimally increases your value by more than the cost. Otherwise, the problem is trivial. So we'll assume that there is a unique amount K that if you invest will maximize your net value. And then the proposition is that for every threshold auction, one of the following 2 applies. And let's just start looking down the left here. Either you invest K or you invest 0. Okay, for every threshold auction. So why is that? Well, if you're going to invest in a threshold auction, your investment doesn't affect your price. If you're going to win, you're going to want to invest the level that maximizes your value minus your cost. And if you're not planning on winning the auction, you should invest 0 since the money is wasted. So one of these 2 possibilities will happen. And what's more interesting, perhaps, is the second part, that you should invest to win if you would be selected to win if your value were V1 of K minus K, given V minus 1. And if you shouldn't invest if you wouldn't be selected when your value is V1 of K minus K. Well, your value is never V1 of K minus K, so why is that the right condition? Well, the reason is this, that this condition that 1 is in V1 of F of V1 of K minus K, that's equivalent to, this is a threshold auction in which you're going to win if your value exceeds a threshold. So that's equivalent to V1 of K minus K exceeds the threshold. And hence, just rearranging, that's the same as saying that V1 of K minus the cost and minus the minus the threshold price is positive. So that says you want to win. Investing is profitable. Okay, and that's if and only if. This is what you get. If you invest and win, this is what you'll get. And if that's not positive, then you don't want to invest. Okay? Yeah.
Winning does not depend on the investments. The question if you win or not. The threshold does not depend if you invest or not.
The threshold doesn't depend on whether you invest or not. It's a threshold auction. The second price auction is an example of a threshold auction. If the second highest bid out there is 50, my value needs to exceed 50. It's a function only of other people's reports. And in general, all of these dominant strategy mechanisms are threshold auctions. My price doesn't depend on anyone else's report. And that's why this simplifies in this way. Okay? Okay. So, and now we want to compare this. Again, we're going to be using approximation mechanisms. We want to compare it to the optimal mechanism. If there is a threshold auction, the Vickrey auction is the threshold auction opt-p-opt. That's the Vickrey auction where you select the set of bidders that maximizes the total value exactly. If we didn't have any trouble computing, that could very well be what we'd want to do. And p-opt is then the VCG prices. Okay, and so the threshold auction, v-opt, is the Vickrey auction. For the Vickrey auction, investment is always efficient. That is, the cost that you want to spend under the optimal mechanism, under the Vickrey auction, is also the thing that maximizes the total social value. And that's because, for those of you who are familiar with Vickrey auctions, the profit that a bidder earns in a Vickrey auction is always equal to his contribution to social value. So the bidder always wants to maximize social value because that also maximizes his own profit. So so this is the optimum for the bidder's problem. This is the optimum for the social problem, and they're equal when the auction's a Vickrey auction. Okay, now the reason now I come to a caution, and this is the reason why we've included only one bidder investing in this problem. Even in the Vickrey auction, if you have multiple bidders, it's not true in general that you get efficient investments. That requires additional conditions. There can be a coordination problem where, for example, in some knapsack, Noam and I could both fit if we both invested. But if he doesn't expect me to invest, then he's not going to invest. And if I don't expect him to invest, I'm not going to invest. There can be a coordination problem in the investment game. And since that can happen even in the efficient allocation, we're abstracting away from that by looking at just one bidder to compare just the effect of replacing optimization with an approximate mechanism instead of using, just replacing optimization with an approximate mechanism. Okay? All right. So if K is the unique solution to maximizing the addition to value minus cost, then the optimum is either 0 or K, and the investment is either 0 or K. So that's going to simplify that'll simplify our analysis quite a bit. It's as if there were only two relevant cost levels to look at. Okay. So how are we going to assess performance now? This is the natural generalization of what you guys always do when you are assessing the performance of, as I've learned from Michal and others. So an allocation function, we're going to say, is a beta approximation for investment if for all V minus 1 and F and all investment technologies delta, the surplus that we get when we take into account the investment that bidder 1 will make, CF with the mechanism F, minus his cost. So this is the net surplus. Surplus minus his cost, taking the investment into account, is at least beta times what we would get from the optimum. Right? I hope this is all natural to everybody. I don't see any reactions. And then there's the easy direction to this. Obviously, if F is a beta approximation for investments, then it's also a beta approximation for the standard allocation problem, because you can just consider the technology delta identically 0, and it just reduces back to your standard allocation problem. So this is a broader class that includes the allocation problem as a special case, but also includes all kinds of investment problems. And we want to know when, regardless of the investment technology, we will still have a beta approximation in the problem. Okay? All right. Now, here are the examples where we see that it's not straightforward and we get in trouble. So this is the simplest example we can think of. Think of a knapsack that has size 2 and 2 items each of size 1. Obviously, it's always optimal to pack both items because we have room for both of them. So here's a family of near optimal allocation functions parameterized by beta. For every beta less than 1, you can consider the function that packs only item 1 if item 1 gets you at least beta fraction of the optimum, and otherwise packs both items. Very simple algorithm. Very simple rule. This rule always gives you a beta approximation, obviously, because whenever it would fail to give you a beta approximation, it selects the optimum. Okay, in the corresponding threshold auction, bidder 1 is always selected, so bidder 1's threshold price is 0. Okay, so bidder 1's always going to participate. Now consider this investment technology where suppose that V2, the value of the second guy, is 1, and the value for bidder 1, if he invests 0, he has a 0 value. If he invests K, he has a value of K plus epsilon. Okay, so what's going to happen? Well, and gamma is going to be the set of such instances, in this case for all K greater than or equal to 0. And at the optimum, you would invest, then you would pack both items, and you would earn a surplus of 1 from bidder 2, and K plus epsilon minus K from bidder 1. You'd have the optimum surplus is 1 plus epsilon. And in the threshold auction, bidder 1 will invest. And if K is large enough, F beta is only going to pack the individual 1, and the net surplus is going to be K plus epsilon minus K, which is epsilon. So the investment performance is arbitrarily bad, epsilon over 1 plus epsilon. So this is just an example to show you that being a good approximation for the allocation problem does not guarantee that you're a good approximation for the investment problem. The investment can be arbitrary. Once you've added investments, the result can be arbitrarily bad. Okay. So we're going to need some more. So near optimal allocations aren't enough. You can always embed the previous example into a standard knapsack problem and extend F beta in a way that preserves relevant properties. It includes this as a special case. So for the standard knapsack problem, we conclude that for all beta less than 1, there exists a monotone allocation function F beta such that I should have mentioned the existence of the omega as well, such that F beta is a beta approximation on this set of problems, and F beta is no more than a 0 approximation for the investment problem. Okay? That's just to summarize that things can be very bad. It's not enough that the allocation that the allocation mechanism work well. Okay, so we want better guarantees, and how do we get them? So here's what we're going to do. This is going to be the extra condition that makes everything work. We're going to say that an allocation function respects improvements if for any pair of instances VF and V prime F, so the constraint sets are the same, but we're just changing the values. Here's the relation between them. Suppose that for each n that was selected in the problem VF, we make the value of item n even higher. So it's even better to pack that item. And suppose that for each item that's not selected, we make the value even lower. So it's even worse to select that item. Then what we require is that the total value under Vn prime of the items we've selected for V has to be no more than the total value when we change to V prime. So basically, we've made V look better. Now that might affect the way our heuristic runs and may cause us to select something else, but it shouldn't make us do worse than doing these things shouldn't make us do worse than if we were had just continued to select as before. Okay, so what's going to happen is when we re-optimize or when we rerun our algorithm and we change what we're selecting, the change is an improvement compared to leaving things unchanged from Vn. So if values are increased for the items that are packed and reduced for the items that are unpacked, the algorithm will find at least a solution that's at least as good as it was finding before for the new value profile V prime. So just here's how it looks in pictures. Suppose that we have, this is opt, and we're imagining we're changing V1, and below this threshold, we wouldn't have selected item 1, so the optimum value as a function of item 1 is flat, And then above this threshold under opt, we would have selected V1. So this is a 45-degree line. And here's the beta approximation where we just scale this thing down by some factor of beta. And here is an example of an algorithm that gives us a beta approximation. It's anything. It could be selecting in ways so that what it's selecting can depend on V1, but it always lies here in between. Now, this example does not respect improvements. Here's an example that does respect improvements. So this one does not respect improvements. This one does respect improvements. As we move away, if we make V1 worse and worse, V1 wasn't being selected. So V1 wasn't being selected before. Oops, that's not quite it. Here's what I want to show. Here is where the algorithm would have started selecting item 1 at this value in this hypothetical example. And as we continue to increase the value, the algorithm might suddenly discover something better and jump up. Or as we reduce the value, the algorithm might discover something better and jump up, but it only jumps up as we move away from this point for V1. It can discover something better. It doesn't forget when we make it more obvious that this is a good choice, it doesn't forget this choice, but it might find something better. So, so some examples is opt respects improvements. Greedy respects improvements. You can show that if you take the value of any of the items and run a greedy algorithm on the knapsack problem, it's going to respect improvements in this way. If you have a bunch of algorithms that all respect improvements, then the max of them also respects improvements. And in particular, M-greedy, which is the maximum of greedy or the biggest single value, that respects improvements. So respecting improvements is a property that at least some of the algorithms that we're interested in does satisfy. And that brings me toward moving toward the main theorem, which is this. Suppose that F is monotone and respects improvements, then if F is a beta approximation for allocation on a set of instances on a problem, then it's also a beta approximation for investment. Okay, so so that's the sort of main theorem of the paper, and I'll remind you again of what respect improvements means, and then show you how this thing is proved. And I think I'm cooking on time here, going pretty quickly. Well, should be all right. So an allocation function again respects improvements if when you make the values higher for the things that are selected and you make the value lower for the things that are not selected, you don't select a worse allocation. You don't find the value that you end up getting in the new problem is not less than the value you would have gotten in the old problem with the old solution. Okay? And here's how the proof goes. Okay, so, and to reduce clutter, there's a lot of ink in the proof. I'm going to suppress the v minus 1, which is constant throughout this thing. And when I look at the investment that the guy makes, I'm just going to call it C hat instead of CF. Okay, so let's see if we can get this started. We're going to start by putting a bound on opt for investments, and it works like this. First, if you take a look at opt, here's the value with investments. We make the optimal investment C star, that's a cost, and then the value that goes in for bidder 1 is V1 of C star. And the first thing to notice is that you can pull the C star inside here. That when you're optimizing, you know, if you think about this thing from the beginning, you can say, well, really the value is V1 of C star minus C star. That is, I can raise the value to that by investing if I wish to do so. And if I don't want to use this thing, I was going to set C star equal to 0 anyway. So whether I want to invest or not, these two things are equal. And this one is, notice that K is greater than or equal to C star. V1 of K minus K is greater than or equal to V1 of C star minus C star because K is bigger than C star. So when you make one of the coefficients larger in an optimization problem, you can only make the value larger. Okay. All right. For F with investments, by the proposition, there are two cases to consider. Either one is in F of V1 K minus K and C hat is equal to K, or one is not in and C hat's equal to 0. So we'll consider the two cases separately. Basically, what the two cases, I should give you some intuition for this before I hit all the mathematics. The intuition is this, that there are sort of two ways that things can go wrong. You can invest when you shouldn't, or you can not invest when you should. And what our condition does is it rules out either of those screwing things up. So in the example I gave you, what happened is in the F beta examples I gave you before, when the bidder invested, the algorithm, which only gives you a beta guarantee of performance, performs much worse after the investment than before the investment. And that's ruled out by our respects improvements property. So here's how it goes. In the first case, we're looking at where the bidder does invest. And what you want to see is, well, the first step, if I can go back here, the first step is that in this case, C hat equals K, so the first equality is obvious. And the second equality is respects improvements, that this is what respect improvement says for this case, that it allows me to pull the K inside the inside here, because I will do I'm going to invest in this case, and I do at least as well. So I'm going to invest in this case, and I do at least as well with the higher value than I do with the lower value. V1 of K minus K is less than V1 of K, and so I do at least as well as I would have done using algorithm F by bringing the K inside. Okay. The second case is when I don't invest and C hat is 0, and again the first equality is just substituting C hat equals 0, and the second equality is respecting improvements again, but now V1 of K minus K is again bigger than V1 of 0, but this is an item that was not being selected, so I have this inequality here. Yeah.
A question. So this condition of respects improvements is just a sufficient condition, right?
I'm going to come to how close it is to necessary shortly. Let me finish the proof here, and the point of the proof is almost finished. So what we have on the left here is the performance with under the algorithm F, and you can see here that that under the algorithm F, this is the optimal thing for the bidder in this circumstance. It's at least as good as using K, and since the K is on the inside here, this is a beta approximation for the allocation problem. So I have this inequality is greater than beta times this, and over here and this should probably just say equals. In the optimization problem, well, if I what have I got here? This is what I proved up at the top here, right? I should have S opt V1 of K.
Yeah.
Isn't it the beta approximation? No.
Yeah, it should be what I have. So so what I have is that the surplus under investment with F over here, and I opt surplus under investment over there, and I have the coefficient beta, so I have the beta approximation. Okay, so as you point out, that's only a sufficient condition. Necessary conditions are hard to come by, and the problem is, of course, that the f can behave very badly if f is guaranteeing me 0.5 of the optimum, and I'm operating in a neighborhood where it's generating 0.9 of the optimum. I can have an investment and that could make things behave much worse, and it still doesn't get me an approximation below 0.5 of the optimum. So getting necessary conditions is going to be tough because it causes I can have investment destroying value in very large amounts as long as I'm in a region where f is performing much better than its minimum guarantee. So in order to get something that resembles a necessary condition, I have to hold f to a bit of a higher standard. So here the idea is we're going to say f weakly respects improvements. And again, this is not a very useful condition because to check it, you have to be able to calculate opt. But the idea, again, is as before, we're going to take a look at an alternative value profile where items that are selected are increased in value. And if n is not selected and it's included in optimal packings, then we reduce its value. And if it doesn't satisfy either of these conditions, we leave it alone. Okay? And then we get the same conclusion. So this in form, if you take out the red stuff, this is exactly the condition I wrote before. And what we're now doing is we're saying, gee, we're doing this only at points where we needed n for the optimum. This stuff where we didn't need n for the optimum, we're not changing. So we're staying there. And the previous proof with small changes works as before. This condition is still sufficient, and this condition is weaker than the condition we had before. And what we're going to get is now is we're going to have for a necessary, so-called necessary theorem. It's actually a Maximal-Domain Theorem. Given two problems, we're going to say that gamma prime is a subproblem if it has a subset of the instances. So example, a knapsack problem with small items is a subproblem of a standard knapsack problem with no constraint on the item sizes. Okay? And we're going to have a discreteness condition, which won't matter to you guys. Doesn't matter to me either, but Shengwu likes it. So the Maximal-Domain Theorem looks like this. Assume that f is a beta approximation on omega, and it's positive, and f is monotone and discrete. If f does not weakly respect improvements, then there exists a subproblem and a beta prime greater than beta. So this is now the trick here is, remember we said things could go, we have something that guarantees you a 0.5 approximation, and the problem is that it behaves really badly when it's achieving 0.9. Say, okay, well, let's restrict attention to the subproblem in which it achieves 0.9 and take a look there. And so there will be a subproblem such that it's a beta prime approximation on the subproblem, and it's not a beta prime approximation for investments on that problem. So what we're doing is we're saying, okay, if there's a subproblem on which this thing performs well, we'll restrict attention to that subproblem and say if it doesn't satisfy this condition, it's going to screw up on that subproblem. Yeah.
Another question about the main theorem.
Yep.
If you have the condition, if the condition holds approximately, meaning that it's only alpha respects investment,
yeah.
So you get alpha beta. Does the proof just extend naturally?
I haven't looked at that. Good question. Not a question. Oops, what happened there? Okay.
So if you have the two conditions, then you have the sum not necessarily smaller than the new sum, but only alpha times.
I mean, it's a great question, and so we could just run through the proof and check the inequalities. I'm not going to attempt to do that in real time, but I think the proof tells us how we would go about approaching that. Anyway, so the point is there's the maximal domain, and so here's a qualitative summary. What I sort of expect people to take away if they don't dig into the detail. So facing complex constraints, in a lot of these problems, we can't compute exactly efficient allocation, so we rely on approximations. But the systems we're designing, and this is the novel part here, interact with the wider economy. We want to know what effect they have on other economic decisions outside of the allocation problem. If a player can invest to raise value, then near optimal monotone allocations alone don't guarantee near optimality for the larger problem, including investments. But if the algorithm respects improvements, that restores the guarantee, the same guarantee that you had for the allocation problem. But our treatment still excludes the coordination problem. And was that my timer? How about that? All right. Good. So that's it. I'm done.
We have time for some questions. Yes.
So you said that you mapped this problem when you were working on the incentive auction.
Mm-hmm.
Could you comment a little bit on the details of that?
Well, so I should comment on the formulation generally, which is, I think, the idea here is that you have to make investments that affect the value of the assets that are being included in an allocation problem, and I gave you a whole list of examples where that comes up. In the TV stations, these guys had certainly made investments and were continuing to make investments in programming and marketing and upgrading their towers and so on, which are physical investments they make, and the value of those investments were going to depend on whether they stayed on the air after the incentive auction. Now, in the incentive auction, the vast majority of TV stations, how many stations did we take off the air, Neil?
More than 200.
About 200, so 10%, something. We took, what's that?
That's an upper bound, yeah.
Yes, so we took fewer than 10% of the stations off the air. So most of the stations were staying on the air. We just packed the stations more efficiently in the available channels. But in all of these allocation problems, the issue is, before you get to the problem, somebody has created these assets that are being allocated. I think obviously we're going to want to get to a Bayesian thing with uncertainty at some point, but this is a first crack at the problem. Other questions?